Okay, folks, so in this lesson we are introducing this idea of the accumulation function. New term, I'll explain what this means here in a second, but I want to note first of all that we're doing the exact same thing in this lesson, believe it or not, that we have in previous lessons, despite this new term here. We're really just introducing a new way of writing this work down. So in previous lessons, I would have, let's say, the integral from, we'll say 4 to 8, right, of f of x dx, and you'd look at the graph and you'd be like, okay, this is negative 12. Okay, right? Now, what we're going to do is instead of writing down this integral with a definite bound, we're going to make a new function. So this is old. This is the old way of doing things. This is the new way. We're going to say we're going to let g of x equal the integral from 4, but instead of upper bound this time, we're going to say the integral from 4 to x of f. And this time we don't want to say f of x because we want to have two different variables here. We're going to say f of t dt. Doesn't really matter except for the notation. Okay. So what this means is it's a function just like we're used to seeing, right? I can change x and see how this function changes. And what I am changing when I change x is no longer the x inside of f. It is the bound of the integral. Okay? So g of 8 would be the integral we just found. 4 to 8. F of, I don't want to say x or 8. I just want to say t again. dt. And then my result is the same. I'm going to look at the graph and I'm going to say that the g of 8 is just the solution to that integral, which is negative 12. Okay. So this is called an accumulation function. So it's when the bound of the integral is the variable that we're changing. So this might be useful to us. Let's say that like f of t is velocity. This accumulation function would represent the distance traveled from 4 to x, and we can change x, right? So this is why this is useful to us, is because we often find situations where we want to represent the total change over a time period and easily have a way to change the time period. Let's find one more g. Let's find g of 0. Okay, so g of 0 would be from 4 to 0, f of t. Now notice we have a backwards integral, right? We have the bigger number on the bottom. We're going to rewrite that. Okay, so from 0 to 4 would be negative 7 plus 3 based on my graph. So it's this area and this area. So that gives us negative 4. Negative 4 though. Should be positive 4. That's it. So that is how we work with these accumulation functions on a very basic level. We'll do just one more example. If you're thinking that this is pretty easy so far, I think that I agree with you. Right? We're starting very easy with these. So in this case, I have g of negative 4. And based on the function that's given, g of negative 4 would be the integral from 8 to negative 4, f of t dt. And notice we have the bigger limit of integration on the bottom again. So I want to rewrite. Okay. And then we need to figure out what this integral is. So let's mark out my bounds from negative 4 to positive 8. So this would be negative parentheses, so that's that front negative. And then 4 minus 8 plus 10 minus 8. So that's just my areas. Positive or negative based on whether they're above or below the x-axis. The result is negative 2, I believe you get, right? Yep. So negative 2 inside the parentheses, and then the double negatives become a positive. And that's all there is to it. Okay. So given this somewhat scary looking thing, I just say g of negative 4 is equal to 2 based on my graph.